zoax.net. Lesson 53, Bitwise Shift Operators. To follow along with this lesson, create an empty console project and add a file named main.cpp to it, as we did in Lesson 1. Before we explain the bitwise shift operators, it is necessary to understand binary number representations. Binary is the method used by computers to represent numbers, using only zeros and ones. For example, an ordinary decimal representation of a number like 237 has digits that are in the range 0 to 9 and are multiplied by powers of 10. The number 237 is 2 times 10 to the 2, or 100, plus 3 times 10 to the 1, or 10, plus 7 times 10 to the 0, or 1. This is the representation of a number that we are used to, and it is called decimal because the digits are multiples of powers of 10. In a binary representation, the digits are all either 0 or 1 and are multiples of powers of 2. In binary, the number 237 is represented as 111011101. So this number is equal to 1 times 2 to the 7 plus 1 times 2 to the 6, and so on. The sum of these powers of 2 is 237, as we expect. The name binary comes from the fact that each digit has two states, 0 or 1. In computers, the name binary digit is shortened to bit. There are four basic unsigned integer types: unsigned char, unsigned short, unsigned int, and unsigned long. These types consist of 8, 16, 32, and 64 bits respectively. Remember that each bit corresponds to a multiple of a power of 2, and since the unsigned char type has 8 bits, it can represent numbers in the range from 0 to 255. The other three integer types can represent larger ranges according to the number of bits that they have. The bitwise shift operators consist of two less than symbols for a left shift, and two greater than symbols for a right shift. These operators shift the bits of a binary number to the left or right. They look exactly like the insertion and extraction operators that we use for input and output. However, the compiler understands the difference based on the context. In our first code example, we create an unsigned int variable and assign it the value 38. Then we output it in binary and decimal format, along with the left-shifted and right-shifted versions. We do the shifting on the passed-in value here. For now, we will ignore the function that prints the numbers and just run the code. Executing the program, we get this. We use 32-bit integers in all of our code examples as we do here, but the other sizes work similarly. Notice that the left-shifted number is twice the original value, and the right-shifted version is half of it. This makes perfect sense if we recall that the digits are multiples of consecutive powers of 2. Also, note that the digit that gets shifted in is a 0 in both the left and right shifts. Now, a funny thing happens if we change to a signed integer type like int. For a positive value like 38, the code works exactly the same way as we see by executing this program. On the other hand, if the value is negative, say negative 38, and we run the program again, we see this. Observe that the left shift shifts a 0 in, while the right shift shifts in a 1. This preserves the doubling and halving properties that we stated before. We remarked that for signed integers, the most significant bit is assigned the negative of its normal value. This means that the most significant bit tells us the sign of the number. If the most significant bit is 1, then the number is negative, otherwise it is positive. This is called the 2's complement representation. To summarize, unsigned integer types shift in zeros for both the left and right shifts, while the signed integer types shift in a 0 for left shifts and a copy of the sign bit for right shifts. Finally, we remarked that we can shift by more than one bit at a time. All we need to do is change the number on the left-hand side of the shift operator. We can shift by any number from 0 to anything less than the number of bits in the integer. We start by assigning a value and then shifting it left by 4 bits and then shifting it right by 19 bits. Executing the program, we see this. One of the things that stands out is that the right-shifted number is largely made up of zeros. Most of the information that was there is lost because the 1 bits have been shifted out. Even in the left shift, we lost some bits of information, and our left-shifted number is smaller than our original, instead of being 16 times it. Even stranger things can happen with signed integers, where a left shift can change the sign bit, and thus the sign of the number. All of this should be kept in mind, as right shifts may lead to truncation, and left shifts to overflow, where doubling and halving properties no longer hold.